So yesterday I was telling you about treating gravitational waves in linearized gravity, and I said there are two ways. One is to treat the gravitational waves as a bit-trick perturbation. The other is to treat them as a quantum field. And these two have different types of expansions. So let me just recollect. So GW as metric. So here what you do is you expand gravitational waves as a perturbation in the metric, and then you say that your strain the detectors is proportional to this gravitational wave. So if you do that and you want to try to calculate gravitational waves from sources, the equation that you get if you start from Einstein-Hilbert action and take it to the leading order, which is quadratic order in h mu nu, is so if you're solving for Einstein wave solutions for this and you have a source, then you use this equation to find out the gravitational wave. And I gave an example where you have a non-relativistic source, the slow moving source, and then we said that this h mu nu is proportional to the quadrupole moment. Okay. So another way is to treat GW as field. Spin 2 bosonic field which is classical to begin with, but you can also quantize it and then derive Feynman diagrams with that. So here the equation is box h mu nu bar again is minus kappa by 2 p mu nu, where this kappa is 32 pi g. And this kappa is fixed by the fact that when you have this equation, if you write start from the Einstein equation and want to get a canonical kinetic term for h mu nu, then you have to, so this is, sorry, I should have written this, expand g mu nu is eta mu nu plus kappa, this kappa, h mu nu. So here, this has mass dimension of 1. Like any bosonic field, and this has the canonical kinetic term. Okay. And in this expansion, you get this equation. So when you have this equation, it means that in the interaction Lagrangian, your interaction is kappa by 2 t mu nu h mu nu. This is the interaction between matter and gravitons. Okay. And so if I want to, so this is h mu nu and this is your t mu nu. So this equation is the same as if you have a charge and it emits a photon, the equation would be J mu times A mu is the interaction. And you can write J mu as a classical and then calculate if there is a change in the velocity, there is a change in J mu, what would be the h mu nu? Sorry, the photon. So the photon equation tells you that the change in the dipole moment associated with this change in velocity of the charge will give you the rate of photon emitted. Here, this equation, if you do it quantum mechanically, will also give you the same equation that you get from here, that change in quadrupole moment. But so if you have slow sources, what you get in this treatment and in the what I derived yesterday would be the same. So the reason being that although we are writing it in the form that you have production of a h mu nu, so it's a field theory way, but it's a tree level diagram. That means there are no loops. And when there are no loops, your results from the classical and quantum always give you the same. It's only the loops which are proportional to h cross, and then you have quantum corrections. Where square root? There is a square root. So this is 1 by mass. So this is 1 by mass. G is 1 by m Planck square. So this is like 1 by m Planck. So kappa times h mu nu. If h mu nu is one mass dimension, then this is dimensionless. So one thing to take away from this is that supposing you have this interaction and you have this gauge. So this gauge choice, that under gauge transformation, h mu nu goes to h mu nu minus, sorry, where this xi mu is the arbitrary function of space time. Then you substitute this here. Okay, this h mu nu. What happens to this interaction term? This interaction term has extra terms of the form T mu nu, del mu xi nu, okay, right? If I shift this with this gauge transformation, then the extra term that you get in the interaction, which is xi dependent, is this, and you want the interactions to be gauge invariant. So for gauge invariance, what you do is, this is in the action. So you can integrate by parts. This d mu you can shift here with a minus sign. Same thing with the d nu. Okay. And what you would like is that d mu t mu nu or d nu t mu nu should be 0. So this is required for gauge invariance. The interaction term is gauge invariance if you have conservation of the stress tensor. All right. Okay, so the bottom line is sometimes we do a calculation in the field theoretic way, but we want to find out what is the gravitational wave signal. So to go from one to the other, all you have to do is multiply or divide by kappa according to the dimensions. Kappa has dimension of 1 by m. So you can check that if you take this equation, divide by a kappa, okay, you will get this equation, where this is h mu nu divided by kappa, that is the new variable dimension. So this is dimensionless. This will have a mass dimension 1 when you divide by kappa. And on this side, you will automatically get from this divide by kappa, you will get kappa by 2. Okay, you can check this. Okay, so which we'll do often, that we do a calculation in field theory and then we say that, okay, what does it mean for a gravitational wave signal? So we will do this. Okay, so now today what I'm going to do is calculate for a relativistic source what is the gravitational wave signal using this one, the first formalism, that is just treating it as a metric. So it's the usual classical way. And then, so this will give me my memory signal. And then I'll also do this soft graviton theorems. It's a big name, but it's a simple relation, or soft graviton amplitudes. And from this, I'll predict I'll extract a signal for this graviton, which will again be the same memory signal. So I'll show you that these two ways of doing things give you the same result. So that second one is the field theoretic way, the soft graviton theorem. This is the field theory. Okay, so let me then start with. So I'll start with this equation, and as I said that Hij is, I think, like 16 pi g lambda ij kl. Okay. And so this is my basic. So this is the metric GI. This is the equation I'm trying to solve. Now here I'm going to talk about a point mass on a trajectory, okay, which is described by xs tau. So this is the trajectory of a point mass. And when I don't put an index, it's a 4 vector. So this x is a 4 vector. Okay. Now, so first we have to find out what is the T mu of that. That is T, let me write in general, alpha beta at a general point x prime is m d tau u alpha. This is okay. So this is the energy momentum tensor, where this u's are and tau is the proper time. So this is given in terms of v, in terms of gamma, where gamma is the Lorentz factor, and I've taken c square 1. So this is the angular momentum for a point particle. So here you can, the way we write it, that this is defined for all space, x prime goes over all space, but it takes non-zero values only at the source because of this delta function. But as a mathematical form, we write it as a function of all space, because when we write the Green's function, we have to integrate over the source distribution. So we will distribute over this x prime, and that will just pick up the trajectory. Okay. Now the Green's function, this I wrote yesterday, was the space part, and so this was the Green's function. So this Green's function is exact. This was not a non-relativistic Green's function. This was a proper Green's function for this box operator. Okay. And then we had taken non-relativistic approximations later. But this is also equal to, so you can look it up in Jackson or some other book. Where this is the 4 vector square. That means the time part square minus the space part square. Okay. So these two are the same. One can go from here to here. So we will take the second version because that is easier to handle. And so this is the observation, X is the observation, and this is the source location. Okay. And so this theta function tells you that this is a retarded Green function. That means observation time is larger than the source emission time, the time when the source emitted the graviton. Okay, so that gives you the retarded Green's function. Okay, so now I use my Green's so if I substitute this Green's function in the, so you can, huh? This one, this one. This term was there, no? This is the Green's function. The mod x by x prime is the 1 by r. Yeah, actually you can just solve this delta function. I'll show you one way. Solve this delta function and you'll see that you'll get that. Write this delta square in terms of just the delta of that function. And you'll get from there. I'll just show you one. Huh? Yeah, delta function of a function. I'll show you right now. I'm doing this. That I'll show you one example and then you'll say this is, I mean, this is basically what will happen. That will work backward to this equation, but in a more covariant way. So I'll recover from this equation, that equation, but in a little more covariant way. Okay, so the Green's function equation means that you are d4 x prime, okay, and the t, the Green's function times t. Okay, so first line is g x prime x t x prime. Okay, and this will give you my Hij. Right? Now I take this t and this Green's function, substitute it here, and what I get is oops, sorry, this is badly written. This one is just this much. Okay, the solution is just the Green's function times the source integrated over x prime, and then I substitute these things g and t, and what I get is 8gm okay. Oh, no. So what, yeah, you are right. The lambda was required there. Lambda, so I should put lambda ij, thank you, kl n, and the source should be kl. And that kl is reflected in this ukul. Thank you. Okay. All right. So now you see that there is a integration over and there is a delta function. So I can use this delta function to remove this one, right? So that was what I meant, that over all space the stress tensor picks up only the trajectory, okay, although it's integrated over all space. Okay. And so it basically remains, so if you will permit me, I will just erase this, or I can keep it. So basically what you need to do here is simplify this now, what I was saying, that go back to the previous step in a more covariant way. So we solve this x minus x prime square, sorry. So this x prime has now become xs tau after removal of the delta function, right? That x prime has become xs. So this is now this is delta t minus tr, I'll tell you what is tr, divided by the function is just the square. So evaluated is tau equal to tau r. So what is tau r? Normally when you have this delta function of a function, that is the delta function of the argument of that function divided by the derivative evaluated at where the function is a 0. So that where the function is 0, x minus xs tau square is equal to 0. This is solved by x0 minus tr okay. And so the solution tell you that this square is equal to that square, and then we take the root where this x0 is larger than xs, because we have a theta function that tells us that the arrival time should be larger than the emission time. So we took the positive root of this. And the place where this equation is met for a general tau is called tau r. Okay. So that is now the retarded time. Actually, earlier we said that tau r is t minus r, but here it is the solution of this equation. Okay, that's the tau r. And so we now evaluate this. So this is equal to, so you just write that again. That is equal to, sorry, I'll evaluate d by, so I get minus 2 x minus xs tau r. I'll first write it tau. Okay, and that minus tau comes from this minus sign. And this is evaluated at tau equal to tau r. Okay, and this is just the velocity. So and I'll write it as now tau r. So this is just the velocity, 4 velocity, and this is the 4 dot, right? Okay, then what I do is I expand that and write this velocity as my, you will see what I'm doing now, is minus gamma s I'll just write it down and you'll see how that works. Where this n is. So From here to here, first you write it as a 1, the zeroth component is 1, the special component is this V. Okay. Then you take the dot product, the first term will be x0 minus x0, right? And the second will be x vector times dot V. Okay. Then use this equation to replace this x0 minus x0s by this mod. Okay. And then take the mod out. When you take the mod out, then this n comes out here because this is x divided by the mod of, and the first term is 1, and this gamma came from this I should write clearly as US, the 4 velocity. Okay? Is everybody clear on these steps? All right. So this is now, I substitute this back and I have a factor of. Okay. Now here, it is still 4 velocity component. So I can write that as a gamma times the 3 velocity. Right? So basically, I have 2 factors of gamma in the numerator, and this, remember, goes in the denominator. So finally, what I have is that, okay, I'll write it. So this is x t. This is 4gn divided by x minus xs tr. Vk. This is not u, this is Vk VL. So since my original had a UKUL, when I turn to the special part, that it has a gamma. Each has a gamma, so there's a gamma square. And the denominator had a 2 gamma s times 1 minus Vs dot. So this is the source velocity. And this, so this came out by pulling that factor out here. So that was the thing that you are asking. Going from that notation to this 1 by x notation, that is the, okay, so this is the answer now for my memory signal. So how is it memory signal? This is actually, this is a formula by Brzezinski Thorne. So this is the expression they give for the gravitational wave which you can expect from a rapidly moving source. Okay. So one example I can give is that, so this is the general expression. Any questions so far? What's the difference between two gammas? Oh, okay, thank you. So what I should do is I should simplify a bit. So yeah, I'm sorry. There was the 8 GM, there was 2 cancelled. So that was 4, and then this cancelled with that, so there is only 1 gamma. Thank you. Yeah, they're the same. So 1 gamma is left. So this is the final expression with the gammas cancelled. And you can write m times gamma as the energy of the source. So so sometimes it's written as an energy. All right, thank you. That was. So let's talk about an example. So this is a real example which people have actually calculated and predicted as a signal. So this is GRB. So GW from So some model of GRB tells you that in the end, what you have is some compact stars rotating around some axis, and then there is a jet. So from GRB jets, or any jet for that matter. So when you have a blob of matter which is produced and thrown out at some velocity v, so this is a jet of matter. Okay, so this has a velocity. So the structure of this is that Vs, so this is a transient phenomena, okay, that it's not an eternal source that is emitting a steady state of matter. I think what happens is that you have two neutron stars which merge, form some sort of black hole which ejects matter. So this is a transient phenomena where one blob of matter is thrown out. So the source velocity is 0 for, let's say, t less than t0, and it is some v s constant for t greater than t0. Okay. So if you now take this and stick that in this equation, that will tell you basically that you have to begin with, there is no source, no velocity, and suddenly as a theta function. So this is basically a theta function, right? Vs times theta. So what you will see basically is a step function in this h when you stick in those velocities, okay, given by this magnitude. And what is the order of h? So if you take m gamma, which is E, which is 10 to the 51 ergs. So this number is calculated on the basis that, let's say you have two neutron stars. Before they merge, they have a binding energy. That binding energy is that much. So that is usually the amount of radiation that you get, for instance, when there is a supernova formed. This much energy is released in neutrinos. So this basic, huh? No, it's not the boost. It is the relativistic formula for energy. For this, oh yeah, okay, you're saying how much boost you have to do. Yeah, it is close to C. It is not C, but it is some fraction of C. No. Why? No, but that depends upon what is M, right? How much M is being ejected. So I think what happens here, like, what is the supernova number? 10 to the 53, right? So 1/100th of your mass gets ejected at relativistic speed. So then you get this number. So, I mean, this is an example they took in this paper. This is I think, Sweep Iran. Look up the papers on this he has written, so you will see the more detail. But I just took the numbers. So if you put in this number, what you get for H is 4G times E by R, and this is your R. Your source distance is, this is small compared to X, then this is simply 1 by X. And this number is 10 to the minus 22 at 1 megaparsec distance. So according to Sweep Iran, this is something which you should be able to observe as a memory signal in some detector. Okay, so basically you see that this signal depends upon V. You give a trajectory and you'll have a V. Here this V had a lot of times what you get is that you have a thing which is produced from zero velocity to some instantaneous velocity. And so in space-time, if you draw a space-time diagram, let's say this is t, this is x, this is my particle trajectory. There was no particle before, and there is suddenly particle with b. That means in time it is a theta function. And so in these velocities, if you put in the theta function, this whole thing means it is zero signal a time before it got ejected, and suddenly you get a constant h. So that is the step. So this is your h. So this is basically t0 minus r, the retarded time, because you are observing it at a distance. Yeah.
So are you saying that it is following the velocity pattern?
It is following the velocity pattern. So normally what happens is that supposing you are saying that supposing there is some other signal. So let us say I have a hyperbolic trajectory, very star coming in and going out at close to speed of light, like what happens in the black. So this is a very ideal signal. This is normal signal goes like that. So there is a step function component in your full signal. So if you calculate it for the actual realistic velocity and write it in a Fourier space, there is a step function and there are oscillations on. Okay. So
the memory signal mimics the source.
not, yeah, of course. Well, it mimics the source, not directly like because the theta function goes to a theta function, but sometimes when you have this like that, there is no obvious theta function, but still you will get a component which is a theta function. So I'll give the game away that in the Fourier mode, the pole, the zero frequency is your memory signal. So if you do a frequency breakup of your H, then the zero frequency component is called the memory signal, but there are other frequencies contribution also. So the total signal is some sort of a complicated oscillator. So that is what we will exploit in when we are trying to extract the memory signal from the field theory part. Yeah.
So if you are looking at the forward direction and velocity is relativistic in the sense
Yeah, yeah.
to see.
Yeah, I know your question.
Divergence over.
Yes, yes. So that's a very good question. So you see, there is what is called a collinear divergence. And this collinear divergence is something which was actually pointed out by Bloch and Norsdick for QED. In 1938, before you had a theory of QED, what they pointed out was that you have this beta decay, okay, or some sort of Coulomb scattering, okay, from a nucleus. So you have a electron gets scattered and you have a photon radiated from there. Okay? And they said that the photon in the forward direction, in the direction of the velocity of the electron, okay, has a singularity which is called the collinear singularity. This is the same structure as this one. And you'll see that also when I do the soft theorems. So the answer to that is that you have to take all orders. So since there are soft photons, you have to take all orders, okay, and then that singularity goes away. Because then if you add up all orders, this goes to the exponent. So it becomes iconal, and then the singularity is solved. Well, it's a complicated thing, but if you follow up this Bloch-Norsdick, the same story is now repeated in GW. That the soft theorem gives you the leading term, but if you want the actual this thing, it's there is exponential, so this collinear singularity is not there. Okay, so now let me just reproduce this in the quantum language. I'll maybe keep this. So I start with this equation now, that my interaction is kappa by 2 h mu nu t mu nu, and t mu nu now these, so I will, okay, so I will write my h mu nu x as sum over the polarizations So this is similar to what you do when you write a scalar field in terms of creation and annihilation operators, except that now you have this polarization vectors, which tells you that there are these two polarization, let's say 1 and 2, but you are writing it in a more covariant way. Okay. So when you write it in a covariant way, you have to do this algebra, you need to work out the properties of this. So those will be that they are orthogonal. This is K and this is K. And they have a completeness relation, which is, okay, I'll write it down here. Lambda equal to 1 and 2. Sum over polarizations of this epsilon mu lambda. So you have these two different, but lambda summed over lambda is so this is the polarization sum, and with this and A dagger have the usual commutation, that A dagger A commutator is delta function of K and K. Okay. So with this you can do field theory of, and if I call this thing P alpha beta mu nu, then basically my graviton propagator h mu nu h alpha beta in momentum space would be just P mu nu alpha beta, that projection, divided by E square. So it's like a massless particle propagator, but there is a numerator, similar to what you have for gauge bosons. So you have these projections for gauge boson, similar as this. Okay, so I'll do now one example of this kind of calculation. So to start with, take, let's say I have a scalar field. So if you do field theory, it's best to, I mean, yeah. Yes, so basically what we do is, this graviton is a perturbation and everything works in Minkowski space. So graviton is a field, just like a scalar field, which is background metric is Minkowski. So all of this is Minkowski. Okay, so if I take a scalar field and write down the Lagrangian, I wrote down the Lagrangian yesterday, and you work out this energy momentum tensor, okay, and take it to momentum space. So I'll just give you the momentum space formula. So I want to take this P1, P2, and this is taking out Q momenta. Okay. So then this T mu nu, so this is I kappa T mu nu, epsilon mu nu of Q. Okay. So the T mu nu is P1 mu, P2 nu, so that would be, if you take the Lagrangian for the scalar field, calculate its energy momentum tensor, taking derivative with respect to eta mu nu, and write it in momentum space for this vertex. So you can check now that Q mu T mu nu, which in this case would be something like P1 minus P2 mu T mu nu should be 0. You can check that later. So this is a sort of a conserved energy momentum tensor. So now I'll get to the heart of this matter. And so this is my what's called the soft graviton amplitudes. So the problem is that supposing you have a scattering which has taken place, so there are n particles, okay, 1, 2, 3, n particles are there in the scattering, both if you include both in and out legs. And then you have a event where you have a graviton emission from any of these legs. Okay. So this is, I'll call this AN, and I'll call this one n plus 1 particle scattering. This is n plus 1 particles in this. So what is the relation between this? So let us say this is a classical event. Here two stars have come and gone, and I want to find out that after this has happened, what is the amplitude for one of them to be radiated, if I know already this. Okay. So the relation is simple, okay, and I'll show you what the relation is. This is AN plus 1. So what do you do here? When you go from here to here, let us say this is P, the momentum here is P plus Q, okay, and Q is going out, and this was P here. So you create a propagator and an extra vertex over this diagram. Okay. So this AN plus 1 is, first I write this for the outgoing graviton, which is epsilon mu kappa by 2. Okay. So this is this vertex times the T mu nu. The T mu nu I'll write as okay, so this is by epsilon times T mu nu, that is the vertex. Okay, you can see this is that P1, P2. P1 is P1, P plus Q, and P2 is P. Okay. And then I have a propagator. The propagator is P plus Q whole square minus m square. This m square is just the mass of this P particle. So P square is m square. Right? External leg, that is your mass shell. q square is 0 because that is your free graviton. Okay. So then this relation in the, and if you collect the numerator, this becomes kappa by 2 epsilon mu nu 2 p mu p nu plus q mu. So p plus q whole square, p square is equal to m square, that cancels the m square, q square is 0. So that just gives you 2 p dot q. Okay. So that is what is left. And now you take the q soft graviton limit. The soft graviton limit tells you that take only the leading order. So q square, q is 0. Take the limit when q goes to 0. So then I drop this term and I'm left with that guy. Okay. So basically this cancels. So the summary is, okay, I should write this totally. So here I've written. And this is not all. This is the new factors you introduce when you started with this amplitude and try to get there. So there is that, multiply that with the old one, an. So that is the full expression, an. Okay. So the n plus 1 amplitude is related, so I should write it in a more. So a n plus 1 is kappa by 2 epsilon mu nu star of q, and p mu p nu divided by p dot q times an. Okay. And you should do it for each leg separately. So I just write there sum over all legs. So call each of these legs separately, PA, PA, PB, PB, and so on till n, and do this factor for n legs, because that graviton can come from any leg. So the total amplitude is n leg. But this is just a kinematic factor multiplying a an. Now supposing this is actually not a honest to goodness quantum scattering, that this is actually not a quantum particle, this is a classical particle. So you have a star, two stars colliding, and you have emission of graviton. And you say that, well, this event has taken place, so this is of equal to 1. So that means this event has taken place. If you want to calculate the full probability of n particles coming and going out as n plus 1 particle, then you have to also calculate this. Write down the processes involved in this. But suppose it's a classical thing and you say this, having this taken, if this has already taken place, then what is the probability of this graviton being emitted? So then this is just that, n equal to 1. So you set n equal to 1 here. Okay, now I am trying to get a signal out of this. Okay, so first let's write down p dot q. This is p0 q0, right? So I'll write p divided by p0. That is just the velocity. So of this classical particle p, relativistic velocity, and q dot q0 is just the direction of the graviton. Graviton has a q0 whose magnitude is q, and the ratio is just the direction of the thing. Okay. And so basically this an plus 1 is now beginning to and so is, supposing I take this kappa by 2 and I now go to only ij components. Okay. This is pi pj divided by, so let me write down, and this pi pj I will write it as, so pi I will write as m gamma vi, and similarly pj, and p0 is m gamma. So you will see that there are gamma squares will cancel, this m square will cancel, and you will be left with, I'll write it here. So it's beginning to look like the thing that you've already seen. Okay. So this is looking like an plus 1 is kappa by 2 epsilon ij, then vi vj m gamma q0 1 minus v dot q, v dot n. So it has a lot of structure of that old expression that I derived, right? So how do you connect this to your observable signal? Okay. So the idea is that, okay, you have this scattering taking place somewhere and you are here at a distance r. Okay. You have worked out the amplitude of this event at that distance r, and you are interested in the signal here, on the actual gravitational wave signal here, not the scalar, not the quantum field. Now you are looking at the signal. So how do you go from there to here? What you do is, from there, this extract a T mu nu effective. Because what does an amplitude give you? This is just the L interaction. Right? It's an interaction term in the Lagrangian. And your interaction term is always kappa by 2 epsilon mu nu times a T mu nu effective of whatever happened. So from that expression, all I will do is extract a T mu nu. So T mu nu would be just the coefficient. Where did I write that? Yeah. So this is my Tij. And notice that this is actually in frequency space, because our currents, how much time do I have? Okay, I'll finish in 5 minutes. Yeah. Okay, I'm done now. Okay. So this leads to a, so at the end of this analysis, what you will do is extract an effective T from here, then go to the old picture where you had this. So effective T, I'll write it down again. Tij is Vi, Vj, M. I think I skipped, I wrote it wrong. So there is a gamma here. Okay. There is a gamma here, gamma square there. So left over there is one gamma there. Okay. And divided by Q0, 1 minus V dot N. in momentum space. Okay. So what you do is you start with your old expression that you have Hij Tt and you say it is 4g lambda Ij KL divided by R, where R is the distance at which that stress tensor is existing. And here I just put my TKL, which I extract from here, and I put it here. So this is basically telling me that I have a effective something going on, which gives me a stress tensor, which is effective stress tensor for the production of that graviton at a distance r. From that, if I want the signal r, sorry, there is no box here. This is the solution. That was, I'm not writing the equation. The equation was 16 pi g, but then there is 1 by 4 pi coming from the Green function, so this is the solution. So in the solution for that, I just put in a TKL. The only drawback now is I have Hij Tt as a function of distance, but not time, it's in the frequency space, because this is still in the frequency. So then all I have to do is convert this into time space by doing a Fourier transform. Okay. So yeah, I will. So my Hij T will be 4g by r, okay, Vi Vj, or let's say lambda Ij KL, Vk VL, and I had a m gamma, and then I take a Fourier transform of whatever is left, which is dq naught upon 2 pi 1 upon q naught e to the I q naught e minus r. So I take the Fourier transform with respect to the retarded time. To extract from that, I had a h as a function of q naught. I take the Fourier transform from that of that right hand side expression in terms of the retarded time. So I want to, so this then becomes a function of that retarded time. And this q naught was part of the pole of that T mu nu. So that was the crux. And use the fact that this is nothing but theta of t minus r. The pole in the frequency space, in the when you take the Fourier transform 1 by q, it is just the heaviside, the step function. So remember that, you see, classically you could deal with any arbitrary velocity by sticking it there. But in this soft theorem, you have a in and out state which are constant momenta, which means that you have only constant velocity. So it's a more simple case. So this one you only get a step function, you don't get these correction terms. But how do you get the correction terms? You get the correction terms by, okay, so the story is that this is your the old formula, Gibbs-Thorne. Thorne. Brzezinski-Thorne formula from the soft theorem, which is, you'll see that once you have done it, it's a 2-minute thing. It's not a, okay. Is there questions so far? Or? Yeah, but normally what we do is, graviton exchange means that what you are saying is that, let's say you have one part this thing and a graviton is, so that is obviously a higher order in kappa, right? We are taking the leading order kappa. If there is a graviton exchange, there is already kappa square. So that will be higher order in kappa. So those are, yeah, second order. Okay, so the summary is that the soft theorems give you the same thing as your memory signal, which is a characteristic of a relativistic particle. And it's not always that just the theta function in the source gives you a theta function in the, because let me give you the full, so Q square corrections to soft theorem. So I'll just write that down and I'll be done. N plus 1 is this is sum over all legs, the same thing you do for the moment at all legs, P mu P nu divided by P dot Q plus P mu Q beta divided by P dot Q AN. So there are corrections. If you keep higher order terms in those diagrams, you will get these, where this J is nothing but the angular momentum of that source. So this is XL alpha E beta, including the spin. If the source is that blob which got ejected, if it has a spin, you can include that spin in this by putting the spin in this. So now you will see that it will not just be because you have this q square dependence. It is not just 1 by q type of pole. It gives you a step function. There are corrections to that. So you will have a more realistic signal as you keep higher and higher terms in q square. Okay. So using this now, you can take this C-Piran example and say, well, if that ejected blob has a spin, what does my H mu nu looks like? What does my signal look like? By including these terms, which I don't, yeah, I'm done. Okay, so that was it. And tomorrow, Sen will tell you that in this memory theorems, there are also some non-trivial log Q0 terms. If you work at higher orders, and those are non-trivial and they have some maybe experimentally reachable. So that was work done by Ladda, Sen and his co. So I have prepared you up till the point when you can follow Sen's lecture tomorrow. Okay, so I'm done. Thank you. Yeah. But I'm sure not lots of energy. By the way, you followed the second part? Anybody? Field theory part? It's a bit rushed because, all right.
So,
Hmm.
so that so we always been told that gravity cannot be quantized. So
Yes.
here you are using quantum field language. So where actually the problem starts to creep in into this?
If you do calculate only tree level processes, like you calculated the exchange of a graviton, even in the propagator, you will get Newton's law, exactly. So only thing is if you have loops, that's a true measure of your quantum nature of graviton. So a loop process or some process where you can see, they show that the loop process is not very highly suppressed, it can be observable. And if you observe it that would be the quantum nature of your graviton. But so far what we are doing is mimic, all these calculations are also done in the standard theory. So we have so far gone up till even I think these log terms have their counterpart in the standard calculations called the tail effect.
So, in a sense, this is not complete, but it works well in that way.
So far it is working well. So the point is that if you want, let's say, a quantum correction, and you are going to, you have the language of this quadrupole, 3 derivatives of quadrupole. So where do you enter there with your quantum corrections? Whereas if you have this language, you can add a term, you can draw a diagram, say this is my quantum correction, calculate it. Easy. So for extrapolations to this quantum regime, this language is easier. So that was the point of these. Also, you see, this, as I said, he was asking that this collinear divergences. So you learn something about this Bloch-Norsdick. In 1938, it pointed out something that, you have to have higher order corrections, which will all exponentiate and so on. So that has to be done here also to get for consistency. So it is possible not just loop correction, but for consistency, you need to use some field theory property of the graviton, which is not there in the classical language. So consistency may demand this quantum, may tell you that this is a quantum.
You have written H mu in terms of A, right? So already quantum.
Yeah, it's quantized, but it reproduces, as I said, a classical diagram, a tree level diagram is only a language of quantum theory. It is not actually a quantum process. Okay, thank you.
If there is no question, let's thank you.
All right, thank you.